So these are two definitions. Something is an even function or something is an odd function. And we're going to look at the graphical representation, what it means graphically, so what the visual of it, but then also algebraically what it means. And you need to know both, okay? You need to know what it would look like in the picture, but also how to figure it out algebraically. So an even function is symmetrical on the y-axis. So what's an example of that? Quadratic, right? We learn about that, the axis of symmetry. It's one of the important properties you learn about in grade 10 about a quadratic. And then absolute value is very similar. It has that same symmetry, right? So those ones, because it's symmetrical on the y-axis, another word we call functions that are like that is, we call it an even function. And notice it has an even exponent. That's not like a necessary part of the process, but it does work that way. Equations or functions with even exponents like that will be even. The ones with odd exponents will be odd. That's where the name came from. So an odd function is a little bit different though. It doesn't have symmetry around the y-axis or around the x-axis. It has what we call rotational symmetry or symmetry through the origin. So I'm going to show you what that means in a minute. Algebraically, going back to even functions, f at x, I'll show you what this means. You probably won't understand it quite yet, but I'll show you what this means. F at x is equal to f at negative x. They're the same. That's another way of saying they're symmetrical around the y-axis. Algebraically, for odd functions, it is f at negative x equals negative f at x. Again, I'll show you what that means in a minute. Okay. What do we mean for an odd function to be have rotational symmetry about the origin? So here is the cubic function. You can see right here what the function is. X to the 3, so it's like y equals x cubed or f at x equals x cubed. You can see that right there. And so that's the function that we're looking at if you're not all that familiar with it. And if I rotate it one full, whoops, doing the wrong one, sorry. Odd. If I rotate it one full rotation around the origin, it's back on top of itself. It looks the same. That's what we mean by rotational symmetry. Does that make sense? And so if I take this back and I go to even and I want this to, I'm not going to be able to do this because I don't have my keyboard up. Darn it. I want this one to be R now. So there is the quadratic. So if it's even and I rotate it, see it rotates back onto itself, right? So it's symmetrical around the y-axis when it's even. Okay, so let's take a look at a couple of easy questions here. Is A, just looking at the picture, even, odd, or neither? Yep, even. Very good. Yep, no, there's no trick questions about this. What do you think about B? Odd. How would you know? Well, visualize it, right? Visualize spinning it around the origin in your head. Does it map back onto itself? Now, I can't tell for sure if this is the exact same point, but you know, it is. Like, we're not trying to trick you or anything like that. What's the graph that we see in C? Yeah, it's sine. So is it even or odd or neither? What do you think? Are you sure this one looks like it's going to map around onto there? If I rotate it?
Would be like the rest of the...
And this one that's down here will rotate up to there. It turns out it is actually odd. We'll talk about this more when we do trig way later in the course. But sine, like we're not worried about the algebra of sine and cosine right now, but it turns out sine is odd, and if you picture cosine, then it's even. Okay, algebraically, what does this look like? So this is an important skill for this unit, just so you know. Here's what I'm going to do. I'm going to find f at negative x, and I'm going to find negative f at x, and I'm just going to compare them and see what they look like. Okay, so f at negative x our first little dabble in this course with function notation. How do we do it? It means I take whatever's in the bracket. So imagine this was like a 2. Then I put 2 in here, right? That's what function notation means. If this was a 10, I put 10 in here. If this was an A, I'd put A in here. If this is negative x, I put negative x in here. And what is negative x cubed? If I simplify that, it's negative x cubed still. You still have the cubed, but it works out to like negative, right? If it started negative, it's going to stay negative. Make sense? And what is negative f at x? Well, that's like negative, and then f at x, which is x cubed, which is just negative x cubed. Therefore, what did I find? Go back to our definition. It will take you a few tries at this until it starts to click. So if you don't get it yet, that's okay, but you need to get it like by the end of the lesson or by the end of the homework. F at negative x, is it equal to f at x? Or is it equal to negative f at x? Or is it equal to neither? F at negative x is the same as negative f at x. Therefore, this is odd, which we already knew. We were expecting that to happen, but there it is shown algebraically. That's how you do it. Let's try another one. We already know what x squared is going to turn out to be. So f at negative x equals negative x all squared, which will give me what? X squared, right? We still need the squared. If you want to do it the long way, it's negative x times negative x. 2 negatives makes a positive, and x times x is x squared. Well, I don't have to do the negative f at x part because I already see the answer, but we can do it just for practice if we want. So f at negative x, watch. So since f at negative x is equal to f at x, it gave me back the original function. Therefore, this is even. What do you think? I'm imagining people are having a hard time seeing what I'm seeing. It looks like there's a lot of confused faces out there. Think about this is f at negative x. We simplified it and that's what we got. It's the same as f at x, the original function. That's how we tell it's even. Let's try another one. F at negative x. You try to do the substitution. What would that look like? Yep.
Question.
Sure.
So on the notes, for the description of the odd function, it has the equation that f at x is equal to negative f at x. That's not right, is it? Like
For
on
odd?
the printed notes, no, it said that, for odd, f of x is equal to negative f of x.
It should say that. If you have that, it's like a typo from a past version or something for some reason. It should say this. So what would this one look like? I get negative x all cubed plus negative x squared. This gives me negative x cubed plus x squared. Yeah? Everybody okay with that? I can see right away it's not the same as f at x, right? F at x is positive x cubed plus x squared. This is negative x cubed plus x squared. They're not the same function. Do you understand? Now it starts to click when you've seen one of each type, I think. What about negative f at x? Let's see if it's odd. That's like negative. And then what is f at x? It's that. How do I simplify this? Negative x cubed minus x squared. So what's my conclusion? It's neither. They're very good. But do you, like, who else is seeing this? Starting to make sense of it?
Could you determine this without running it like through these calculations?
You might be able to, but you can't convince me that you did it and did it properly without showing your work, like everything, right? Questions? Okay, try these. I don't know that you really need to do extra steps for this one, but this works out to plus x cubed like that. And then when I do negative f at x, I get negative x to the fifth minus x cubed, which is negative x to the fifth plus x cubed. Therefore, you should have got odd for this one. This one worked out to odd. I'll show you this one visually in a moment. F at negative x equals negative x to the fourth plus 2 at negative x cubed. If this isn't clicking for you yet, try to separate, like, is it the subbing in negative x and how you do the algebra to work out, like, how it actually works out that you're having trouble with? If that's it, just practice a little bit more. That should click. Like, that's fairly simple algebra. Negative x times negative x times negative x. That's all we're doing, right? If it's the idea of what an even and what an odd function is that you're struggling with, that's a different story. Okay, so this works out to negative x all to the fourth is x to the fourth minus 2x cubed. Therefore, well, we haven't quite solved it yet, but what's this one going to work out to? Cameron, yeah? At the end of the period? Oh, right now? That'll be most possible. Okay, so let's figure out this next one. Negative f at x equals negative x to the fourth minus 2x cubed. It flips the sign of everything, and it's neither. Okay, so let's take a look at a few of these. We got a little bit more to do, so I'm going to hurry through this a little bit. We saw, let's take a look at x. Is it even? Does it have symmetry across the y-axis? Nope. Is it odd? Yep, there you go. And it's got an odd, like it's an odd degree function. But what if I made it x plus 3? Well, now it's not. Right? So we're only talking the parent functions here, and we're talking even and odd of the functions, right? That's not symmetrical. So x plus 3 is neither. But just x is odd. That goes for all of them. So let's see, what was another one that we did here? X to the 5 minus x cubed. What does that even look like? Interesting. So we first checked, is it even? No, not the same. Let's check if it's odd. Yep, matches our algebra. Way better. Right? Like graphing like this is not something you need to be able to do, by the way. We're just thinking about the visual of what the symmetry means, right? And then what was the next one? It was x to the fourth plus 2x cubed. Was that right? Yeah. Oops, put this back. So that's what it looks like. Got a weird little lump in it. You can tell it's not symmetrical anymore. Even though it's a degree 4 function, like the highest degree is 4, it doesn't work. And is it odd? No, definitely not. What if I change this to x squared? Well, now it is. You may think you can predict just by looking at the equation. In some cases, it might be as simple as you can, but you need to show your work just because that's what we do in school. But also, it's not always as obvious as you might think. Again, if I make it just x squared, whoops, then it certainly is even, as we've talked about. But if I make it like 2x plus 1 squared minus 3, then it's definitely not even or odd. So you transform it and things kind of fall apart. That often happens with this even and odd stuff. Okay, moving on. Here's our graphs of the base functions. I'm going to do these really quickly. If you don't have it copied down yet, like if you can't keep up, don't worry. Okay, you need to be able to do these, but you don't have to necessarily have them drawn out this minute. This is what I was talking about before, like working memory. You want to know these functions inside and out. So it starts at 0. I mean, this one's pretty easy. I think I said this yesterday. It's really hard to draw graphs on this computer screen. So that's the best I can do. Okay. Piece of paper is a lot easier for some reason. It's just slippery. There's my parabola. No transformations. These are the parent functions. Oh, reciprocal. So if I put 1 in for x, I get 1 out for y. If I put 2 in for x, I get a half. 3 in, and then it's symmetrical that way. Arrows, and then same thing on this side. And we're just sketching. Reciprocal function is such a pain. It's so hard to draw accurately. Okay, absolute value. I know it starts here. I put 1 in, I get 1. I put 2 in, I get 2. I put 3 in, I get 3. Put negative 1 in, I still get positive 1, positive 2, positive 3. So it goes out like that. And it goes out like that. Square root function, we talked about this one before. Square root of 0 is 0. I go over 1, square root of 1 is 1. Over 2, no good. 3, no good. 4, no good. Square root of 4 is 2. Over 9, square root of 9 is 3. And there's my parent function. And then 2 to the x. So 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. These are all from grade 11. Sign starts here. At 90, it's at 1. 180, it's at 0. 270, it's back at 1. 360, it's back at 0. And continues, if I wanted it to, ... Like that. Okay, so what was the point of all that? We're going to talk about the characteristics, try to understand what all of these properties are. There's a whole bunch of them. Domain and range we've done. What is the domain of just f at x? X can be anything. What's the range? Y can be anything. Goes up forever, goes down forever, goes right forever, goes left forever. These are just the parent functions. What is the, what are the zeros? 0, 0. It only has 1. And the y-intercept is also 0, 0. Not very interesting. You guys know what the zeros are, what the x-intercepts are, what the y-intercepts are. Interval of increase. I don't have a definition for this. I should. Interval of increase or decrease. We always go left to right. So in other words, this is a little bit strange, I know, but your x's start at like negative infinity as far back as you can possibly go. And you move to the right. This is my right. This is kind of your left, I know. Okay. And are the y's getting bigger or are they getting smaller? Okay, so always go left to right. Are the y's increasing or decreasing? That's what it means. Yes?
How would it look for quadratic because it's first decreasing?
Yeah, so we're going to talk about that. Yeah. So there's also a notation thing, and we use a round bracket is exclusive. Just write this down. I know it doesn't make any sense to you. It will in a minute, hopefully. And a square bracket is inclusive. This is a new way of writing, a new notation. Everybody got that? So, as I go left to right for just a linear function, what's happening? Zoe? The y's are increasing by 1 as I go over 1, but that part, the specifics don't even matter. So the fact that you said the y's are increasing, that's what we're looking for. Forever, right? Forever. So this is how we would write that. We start at negative infinity. That wasn't a very good infinity. And it goes to positive infinity. And I use round brackets because those are not actual values that you can include. What is the interval of decrease? Never. It never decreases. So I don't know, write never, write NA, write something like that. Or even just a line. Is it even or odd? Oh, now we gotta remember that. Odd? Vertical asymptote, horizontal asymptote. No. We'll talk about what asymptotes are in a moment if we get to it. 15 minutes left. Oh, here's another new notation. Okay, this is called end behavior. I'm going to write that down. And I know this is a lot. Don't worry. You got to work through it. You'll get there. This is a little bit different. You could almost think, well, it's not quite. Oh, zoom out a little bit here. Okay, this is called end behavior. So take a look at what that end is doing. Where's it going? It's going way up into quadrant 1. Right? It's going out to quadrant 1. In fact, sometimes we talk about quadrants when we talk about end behavior, but we're not going to do that today. What's this end doing? It's going way down there. Okay? Down to quadrant 3. So what it's asking here, as x goes to positive infinity, so x is going out to positive infinity, what's y doing? It's going to positive infinity as well. Do you agree? Do you see how that's happening? As x goes to negative infinity, that's the next one in our table, the last one. What's y doing? It's going to negative infinity. Good, thank you, that's right. It's going to negative infinity. That's what we call end behavior. It's different from increasing and decreasing. It's related in some ways for sure, but not the same thing. It's another way. Remember I talked about this, was it yesterday or a couple days ago, about like describing a person. They have brown hair, they have blonde hair, they have red hair, they have black hair, that kind of thing. This is another way that we can describe functions, different from each other. What's the end behavior? Well, this one's going like this. What's this end behavior? Oh, they're both going like this. What's this end behavior? Oh, geez, I don't know what's going on now. What's this end behavior? It's different, right? They're all a little bit different. Okay, so let's write it down. Here's our notation for end behavior. This one's a bit probably easier than interval notation. As x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, remember this is for our linear parent function, y goes to negative infinity as well. Anybody panicking? Thinking that they need to rethink the choices that they've made with their life. This is not a course for the faint of heart. This is one of the hardest courses in all of high school. You came here, you got to work. It does move fast. You do need to learn quickly. But I'm here to help if you're sticking it out. What's the domain for a quadratic function? What x's can I put in that give me some y value? X can be anything. What about y? Y is an element of the real numbers such that y is always greater than or equal to 0. Like, I know these are easy, but we're reminding ourselves, some of these are easy, but we're reminding ourselves of how we describe these different functions. And then we get to look at this chart and we get to say, how are they the same? How are they different? Which ones are the same? Which ones are different? Which ones have a lot of similarities? Which ones don't? Okay, so zeros, again, it's 0, 0. Y-intercept, 0, 0. Okay, so this was the question asked earlier. What happens for the interval of increase and interval of decrease? As I start from negative infinity and come across, what's happening? Y's are getting smaller and smaller and smaller and smaller and smaller. I hit 0. And it changes direction and they get bigger and bigger and bigger and bigger. So what's my interval of increase from 0 to positive infinity, because it will increase forever? What's my interval of decrease from negative infinity to 0? I used round brackets for both because at 0, it's actually not really increasing or decreasing. It's flat, although this is somewhat debated, but it's not. But That's more of a calculus discussion than a functions discussion. So we don't need to worry about it. So I did if you're observant, you notice I use round brackets for the 0 and the infinity. But with numbers, sometimes we don't. But in this case, I did. Even or odd, we've done this even. No asymptotes. Okay, here's another good one. As x goes to positive infinity, y goes to positive infinity. And the next question, as x goes to negative infinity, what is the end behavior? Y goes to also positive infinity. So see how now this time they're a bit different. And they look different. One's pointing up and down, the other's both pointing up, right? So how we describe the graphs. Reciprocal function. Who remembers the domain and range for reciprocal function? X is an element of the real numbers such that, can x be anything? No, x can be almost anything except for 0 because it has an asymptote there. That's what an asymptote is. So we write that as x cannot equal 0. And it's the same range. The parent function, if I transform it, it certainly can have x-intercepts and y-intercepts. But parent function actually doesn't have any. Never crosses the axis. Interval of increase. We don't have a lot of time, but I want you to think about this. Try to answer this yourself. What's the interval of increase? What's the interval of decrease? So what you're doing is you're imagining like a little dot coming from negative infinity and going across the function. What's happening to the y's? The x's are getting bigger, 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 bigger. That's by definition. Interval of increase, decrease. X's are always getting bigger. What's happening to the y's? The y's are getting bigger? Getting smaller. Yeah, it's just the other way around. It's getting smaller. Right. So interval of increase, is it ever increasing? Because then all of a sudden it doesn't do anything because it doesn't exist. And then it starts again up here. It's still getting smaller. Still getting smaller and smaller and smaller. Is it going to start going up again? No. Right? So this has no interval of increase. And its interval of decrease is everything. You don't have to use interval notation necessarily here. Like you might see this written as this. X is an element of the real numbers. Like you could write it in this set notation as well. I mean, there's nothing wrong with that, but interval notation is something that the textbook uses at this part. And it's something we do need to know eventually. Yes?
Would you write anything to show that x 0 is excluded?
No, not in this case. Even or odd? See, now we're thinking. Odd. And prove it. Of course, it's odd. Right? Good. Yes, it has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. As x goes to negative infinity, this is hard, this is a bit tricky. What does y go to? What do you think? Y approaches 0. Very good. It doesn't go to infinity. End behavior doesn't always have to go to infinity. And as x goes to negative infinity, see, now I'm going the other way. I'm not increasing or decreasing anymore. So now I'm going this way. As x goes to negative infinity, again, y approaches 0. From the bottom this time. In this case, it's approaching 0 from the top, and in this case, it's approaching 0 from the bottom. That is an actual notation we use, but you don't need to worry about it yet. We do that in a unit way down the road. Okay, so here's what I'm going to do. I'm going to stop. I'm going to do the last 3. I'll even do it as a video, and I'll put it up if you want to watch it. But I think you can probably do the last 3 on your own. I would encourage you to try and see if you get the right answers, and we can compare tomorrow, or you can just look it up. I'll post it as a PDF, and I'll try to even do a video. But I'm going to give you, we only have 5 minutes left. I'm going to give you 5 minutes to start the work if there's any other questions or anything like that.